So, which means inductor should be able to support minimum 1.14 peak current actually. Okay. So, inductor has two specs. It has a RMS current and saturation current. When say RMS, sometimes they call it I rated DC, and that is based on the temperature rise. And I sat or I saturated current is based on inductor's core saturation. Okay, and that will be the worst case. So, when your inductor is saturated, it is gone actually. I mean, usually your inductor looks like this. So, if this is your I load and this is your L. So, let us see if I am looking at .7L, this is called I sat. When your inductor drops by 30%, okay, and then you have another curve I load temperature rise. So, this is your 40 degree C. Temperature rise means extra temperature from your whatever temperature you are measuring at. Okay. So, if you are measuring at room temperature, then room temperature plus 40 degree. If you are measuring at, let us say, the 100 degree C, then it should be 140 in that case. So, I will call it delta T. So, this is defined as IDC or I rated. So, let us see. Okay. So, first let us look at the capacitor. So, if you remember, I mentioned about the voltage derating and your resonance. So, resonance will happen if a capacitor has a inductance. So, just like a equivalent series resistance ESR, you have a ESL equivalent series. So, you can think about your it is a series LCR, nothing, the capacitor, then series R and series L. So, it will have some resonance, and at that resonance what will happen? Your impedance will be same as your resistance. So, this is your ESR, this bottom point, okay. And you can see this ESR is exactly overlapping with the bottom of your resonance, okay. So, I mean ideally you want this curve to keep going, but this is happening due to the inductance. At higher frequency your impedance will be high because of the inductance, okay. But if there is no inductance, then what will happen? It will be limited by your ESR, okay. So, it will flatten out, but ESR is also usually a function of your frequency, and that is why it is changing, okay. Temperature behavior is not that bad, you can see its temperature is not change, temperature is not causing much change in the, so hardly 10% or so. But you look at this is your DC voltage. So, here your capacitor is 0% at 0 volt, at 2 volt it is dropped below 20%, and below 20% means 80% of the total value, and here you see 80%, around 20% is left at 8 volt, like 5 times reduction. So, you have to be a bit careful when you are choosing the cap, and what is the rated voltage of this? 10 volt. So when you are very close to this, like 8 volt or beyond, you might not get any cap actually. I mean 10 microfarad will become like a 1 or 2 microfarad only. So you will not meet your ripple spec in that case. So which means you have to put 4 or 5 caps in parallel these. Okay, I mean usually you put in the parallel, the reason is if you just take a single cap of 100 microfarad, the ESR will be much high and ESL will also be high. But when you connect in parallel, your ESR, ESL both will be in parallel and they will get divided. So, you will get a better effective cap compared to the other case. Okay, so let us look at the inductor. Okay, this. So, these are the different values. So, starting from 0.33 microhenry going up to 4.7, and you can see how the DCR is changing. So, the lower inductor has a lower. Now, think about 165 nano, half of this. So, DCR may be like 12 milliohm or so. Okay. So, if you look at 2x of this, I mean it is not scaling 2x, but still you might see less than 20 milliohm there. And what we considered in our calculation? 50 milliohm. So, 50 milliohm is actually much higher we considered. Usually for those values of inductance you will not have, but for 1 micro 1 megahertz the value was 1.65. So, 1.65 you can see here. So, approximately we were, so the 50 milliohm we chose actually for this particular, but we kept the same for lower. So, it will not harm anything actually, your efficiency will look even better, okay, because your conduction losses will be much lower in the inductor compared to the 50 milliohm DCR. So, now you have two values here, you can see delta L by L 30%. Okay, so, this is your ISAT, that is what we define, and now look at ISAT for this lower value. As the inductor goes lower, your ISAT improves and your I rated also improves, because I rated is based on temperature rise and temperature will increase only when I square R losses are there. So, if DCR is high, then temperature rise will be more. So, which means lower DCR will improve your I rated DC actually. So, you can see if you choose 4.7 microhenry, then we cannot. So, in that case I mean supporting 1 amp will be like you are at the edge roughly. So, you have to be a bit careful when you are choosing the inductor. This all when say 2520 means 22.5 milli mm is the length and width is 2 millimeter and 12 is 1.2 millimeter height. Okay. So, the package also depends. So, let us say if you are looking same value inductor in a smaller package, so all the specs will change, because smaller size means your thickness of the coil, okay, and everything will change and your DCR will increase. So, that is why if you look at a power inductors, I mean the same let us say 1 microhenry I am looking at 10 milliohm kind of a DCR, your inductor will be really big actually, and you can look at any converter which is catering to 10 amp kind of current, you can see the inductor will be the biggest component in that. Okay, but for cell phone application and all those we cannot have that big capacitor. I mean the height, it is mostly limited by height because your phone thickness is limited. Okay. And your board size also, if you open your phone you will see the board will hardly occupy like even 20-25% of the total real estate which is, because battery is almost occupies your 40% kind of a space, then you are left very limited space for your, because in that leftover space you have to place your speaker, you have to place all other your camera and everything actually. So, you cannot put a very big inductor there. Okay. So, usually 20-20, 25-20 are these package size you use for cell phone applications. So the biggest inductor you might see in the battery charger actually, because that's where we charge, especially fast charging and all those requires very high current. So that's why. So you can see here, this is your inductance value dropping as you increase the. So and this is for 0.33 or so inductance, yeah, 33. So 30% when it drops, that will give you the, and your, I mean I just drew the linear, but it's not exactly linear, it's not linear, but just to give you an idea that it will increase. So when it reaches 40 degrees, okay, and if you look at any spec, the reason 40-degree rise we choose because most of these materials are defined like max to handle maximum temperature of 125 degrees C also. And if you take any data sheet of any product, you will see the ambient temperature maximum they will define 85 degrees or so. You can look at it. So 85 plus 40 is nothing but 125. So beyond that we cannot guarantee operation. Your inductor may even break actually. So this temperature rise is still may be okay, but and saturation there are two types. This is a soft saturation. You can see it's not this curve is not that steeper. What I have drawn here. So this is actually hard saturation, and this one is a soft saturation, and the hard saturation mostly happens if you have a magnetic core. If you have a non-magnetic core, let us say air core or even metal core, then you will see a soft saturation, and most of these inductors, smaller package inductors, they will have a soft saturation because they do not have a magnetic core. Magnetic core inductors are really big and they are not feasible to implement in a smaller package, and that is why if you look at any power inductor, you will find your saturation curve like this. So for that, those kind of inductors, you have to be a bit careful. You have to have enough margin, because the moment it hits your saturation, your inductor will drop quickly. It will increase your peak current. So let us say 1 microhenry and it drops to 100 nano, 10 times increase in the peak current, it will break everything FET, and that is one of the reasons you require that current limit, because so that you can turn off your FET immediately and protect the inductor as well as power FET everything. Okay. We were talking about this inductor and capacitor, how you choose that, how you look for I rated and I saturated or saturated current for the inductor. So the saturated current was when the inductor drops, value drops by 30%, and DC rated current is when the temperature rises by 48 degrees. So there is something called self resonance in the inductance. So because these inductance will have parasitic caps, if we remember the models we talked about. So based on that parasitic caps, they will have a self resonance. So when you choose an inductor, you have to make sure that your self resonance of this inductance is much higher than your switching frequency, otherwise you won't get any value of the inductance. So basically that inductance is dead when it's resonating. So those were the things you need to consider. Other thing we talked about ESL in the cap. So this is your RESR and this is your LESL. So it has omega naught 1 over square root LC. And your inductance will be looking like, the impedance. So if this is your frequency,
the self-resonance frequency of inductor should be much greater than series frequency, but sir, after resonance frequency only the inductive part starts dominating and
No, no, it's not like that actually. So usually in the inductance, if you look at the curve, it's like this. Okay, so inductance value will drop very quickly after that, because that capacitor will be in parallel, and at high frequency it will short and you won't get any inductance value. So this is nothing but RESR. Okay. So you have to be a bit careful. I mean, you want your capacitor to behave as a capacitor, huh? So which means if you look at beyond omega naught, it's behaving like inductance, and you don't want to. So this omega naught should be higher, much higher compared to your resonance frequency. Otherwise, your ripple performance will be very bad. I mean, your output ripple would be quite large. So this is the one thing. Other thing is when you are placing the cap. So this is your chip. So let's say these are your pads. I'm not drawing all the pads, just few pads. So this is your DC to DC converter chip. So internally you will have a power FETs, and let's say this is your VSW node. So you will have inductor here. You will be placing the inductance. The inductor, and let me just draw the symbol. So, and this is your cap. Okay. So what you are looking ESL here. This ESL is, this is LESL, this is RESR. Okay. So when you are connecting your capacitor to inductor from output actually, okay, so from output to the capacitor end, when you are drawing the trace, you have to make sure that trace is minimized, the trace length. Otherwise, that will also add some inductance, and it will be added with your LESL. Okay, so that's why you have to place the connection to V out node. So when you are taking the load, so this is your system. Let's say this is your system. System load, and this is your V out. So when you are connecting the cap, you have to make sure this capacitor is closer to your system. Okay, so that's the one thing you want to avoid, the R also. Okay, or wherever V out you are connecting this, so it will be placing close to this trace actually. So it will be more looking like a star connected. Okay, so that you get a effective cap. So your ripple will go, inductor ripple will go and will get absorbed in the capacitor. So you don't want to have this large L in the inductor current or ripple current path. So that portion you have to minimize. So because this is your delta IL which is flowing into this, and that's why we try to reduce the inductance. And when you are looking at a VDD side, so if this is your VDD, and you know that what will be the current profile at VDD, we have looked at it, huh? that will be like a pulsing current, or completely on off. So you need a even more effective cap here, because the ripple current here is continuous, but you have more discontinuity in the on the VDD side, and you look at a amount of the current, switching current which is flowing into VDD is, or outside VDD is much larger. It will go 0 to all the way to load plus your ripple if you look at the peak. So in that case you cannot even afford to have a longer trace here when you are connecting the capacitor. So, and this we call it C-in. So you have to put this decoupling cap at the input always. Without this it will not work. So if you have a larger inductance, and all those switching currents will be supplied by this capacitor. So your, we know VL equal to L di by dt. Now let's take an example. L is 1 nanohenry and your di is, let's say, 1 amp, and dt is, and we know we are rising very fast, so let's say 1 nanosecond. So what will be VL? 1 volt, which means the overshoot undershoot, it will cause basically a kind of a ringing, because it will resonate when you have inductance, and this LDI by dt, or the voltage if you look at across that inductor, will be much higher. So you are having a VDD of 1.8 volt. On top of that you might see plus minus 1 volt undershoot overshoot when it rings, and which will make it going 2.8 volt, and so lower voltage may not be a problem from reliability point of view. The worst case, what will do, your system will not work. But when you look at a higher side, it will cross the breakdown voltages of your devices, and that may break. So that's why this is very important. When you are connecting the capacitor with a large di by dt, then you have to make sure that your ESL is very small. If that ESL is large, so which means if, let's say, if I can afford maybe plus minus 100 millivolt or so, so in that case the value of L you require here, the equivalent series resistor or parasitic equivalent series inductance or parasitic inductance associated with that C-in, which will not include the inductance of C-in itself. When I say LESL is inherent to C, but whenever you are connecting this capacitor to your VDD node or any other pin, that trace will also add, because that will be in series with LESL. So the total inductance we are looking at is maybe 100 picofarad or picohenry or so in this case. Okay. So, and that's one of the reasons if you want to minimize this LESL, you connect more number of caps in parallel rather than putting one single cap. Okay. So that's a one way. So most of the time what happens, your chip size is not that big here, and these pins are very closely packed. So it's very difficult to move the cap, bigger cap, as close as possible to the pin. So what you do actually, so let's say if I am looking at a VDD, because that is more critical in terms of ripple if we talk about, and this is the capacitor you are putting. C-in. So what we do, we put, and if this is, let's say, large cap, to move closer to, or I would say to place closer to VDD pin due to limited space. But if I have a smaller cap, then I can put it. So what you do, you use two caps, let's say C-in 1 and C-in 2. So if C-in 2 is, let's say, 4.7 microfarad or so, then this you can keep maybe 100 nanofarad So, if you look at the size, compare the size, this may be like this size and this guy will be this size. Okay. So, this can be easily placed closer to pin compared to. So, what you do, you first place a smaller cap and then next to that you put bigger cap. So, what would happen now, you will have two resonance. Okay. So, two resonance means your curve will look like this. Again, if we have omega, and obviously the lower frequency resonance will be coming from the bigger cap, and then you will have, so let us say my higher frequency is looking like this. So, effectively what you are looking at higher frequency, it's your impedance is not always increasing, because this will be looking. So, the effective capacitance, if you are looking here, it will look like a more cap compared to the one single cap. Okay. So, this is a more effective way of placing the cap if there is a risk of having larger ESL. Okay. Even so, and your this ESR will also come in parallel, so that will also get reduced. So, it will basically benefit you in both the ways, in ESL as well as ESR. So, that is how most of the time we do when you are placing the capacitor around your chip at a system level. Okay. So, this is very important. If you do not care about this, then there is a risk that your device may fail or it may break. Okay, because 2.8 volt or 1.8 volt devices cannot tolerate, it will damage right away. And we cannot slow down the edges. I mean, one way is like you just slow down the di by dt by increasing the rise and fall time of those currents. By doing that, basically you will be degrading the efficiency and limiting your duty cycle also, because if your rise and fall time is more, then that will limit your duty cycle, and your switching losses may also increase. If you remember the triangular one, that will stretch, so and that loss will also increase. So, we want that switch to turn on as fast as possible. Okay, so when we talk about the top level considerations, layout consideration, we will also talk about EMI and all those caused by this, because this current will be injected in. This is the one is the VDD case, other is the ground also, because bottom FET is also turning on. So, you care about that inductance as well. So, when you are placing your FETs, you have to make sure that when you are routing those FET and connecting to the ground, that should not have a inductance, because series inductance in that FET, that will be looking at a series with the source of your bottom FET, and then at the source you will again see that this LDI by dt noise, and that may again damage that FET. So, you have to care about that as well.